All right, so correct answer for this. We talked about byte short, int, and long last time. And this was related to the Y2K problem where memory was at a shortage years and years ago. So a lot of early programs were written with 2-year dates instead of 4-year dates. And that was because memory was expensive. So why do we have so many different ways of holding positive and negative whole integers? So that we can be as memory efficient as possible. Remember, with bytes, we can hold a range of negative 128 to positive 127. So if we know we don't need to hold a number outside of that range, if we're only counting from 1 to 10, for example, we only have to use 8 bits or 1 byte of memory to hold our value, rather than 16 bits, 32 bits, or 64 bits. Smaller memory footprint. Make sense? Okay? So historically, we needed to be good stewards of our memory and pick the right type of primitive to hold the range of values we expect to hold. Modernly, we typically will use an int. If that's not enough, we'll use a long. All right, questions about that? Okay. So, last time we talked about, just as a follow-up question for in class, why are chars unsigned, but all of these guys are signed? So why does byte, short, int, and long allow us to hold positive and negative numbers, but chars allow us to hold only positive numbers? Go ahead.
Because chars see everything as letters.
Okay, tell me more about that.
With signed letters, there's not. You are squaring things, but it's not. With chars, it's only positive numbers, which leads to letters.
Okay, so letters and characters and question marks and different symbols, right? Okay, so we talked last time about ASCII and Unicode. What are these guys? These guys are character maps. Okay, so character sets. ASCII has 256 unique characters. Unicode has 65,536 unique characters. So what we have is this big list where at each position in the list we have a number. So there's a character at position 0, there's a character at position 1, there's a character at position 2. We don't need to hold negative numbers because all of the characters start at bucket 0 and go on to 65,535. Okay, so in the char primitive type, this guy, we are holding numbers which map to characters on the Unicode, or an older language would be the ASCII character set. Make sense? Okay, so even though chars are built for holding numbers, those numbers are used in a very specific way, and that is to map to an actual character on the Unicode character set. And those characters aren't at position -5 or anything like that. They start at bucket 0 and go on to 65,535. Okay, so that's chars. We talked about ASCII and Unicode. So ASCII is the older one, only able to hold kind of English type symbols. Unicode is more welcoming to all the languages this world has. So Unicode would be what most languages today use. All right, so now we get to our float and double primitive types. Floats hold decimal point values like 3.14, stuff like that, where where an int would not be capable of that. An int, if you tried to put the number 3.14 inside of an integer, it would store the number 3. If you tried to put the number 3.9 inside of an integer, it would store the number 3. It won't do any magical rounding. It does what's called truncating. It's not capable of holding decimal points and the stuff that comes after them. So it'll just cut it off, truncate. Floats can hold what comes before the decimal point as well as what comes after the decimal point. Typically, floats are 32-bit signed integers followed by 16-bit unsigned integers. And what I mean by that is we have 32 bits before the decimal point that has a sign. So we get 2 to the 31st power. That's negative plus or minus 2 billion. Very similar to integers, this guy. But what comes after the decimal point is an unsigned 16-bit number, 2 to the 16th power. Because you would never have negative numbers after the decimal point, right? Okay, so a float is 48 total bits in most languages. But from what I want you to understand here is that floats are smaller than doubles. So float is the decimal point version of ints. It can hold smaller values than a double can, just like an int can hold smaller values than a long can. All right. So a double has 64 bits, signed integers, before the decimal point, 16-bit, unsigned integers after. Okay, so they both share this limitation of 16 bits after the decimal point, because all that has to do with precision, right? When you need to hold a larger floating point value, typically it's not because you need more precision, it's because you need a larger value before the decimal point. Okay? In any of these cases, the people who made the language basically just pick these numbers not out of the sky. They're still a power of 2. We talked about converting numbers last time, didn't we? Yep. I would expect a quiz at some point about converting a binary number to decimal. That would be I like asking those. So last time we looked at how to convert these numbers and that kind of stuff. So a double, 64-bit before the decimal point, 16-bit after. A float, 32-bit before, 16-bit after. Make sense? So those are our 2 ways of holding decimal point values. Booleans hold whole integers. And these guys are probably the most variable across languages. Historically, well, a Boolean value we typically think of, and we're going to talk about Boolean expressions today. A Boolean value is typically either true or false. Okay, it allows us to ask questions. So kind of that's where we're going with this. All right, we need Boolean values in order to ask questions. So it's typically either true or false. Well, that true or false has to be implemented somehow under the hood. Just like chars are implemented as numbers under the hood, we think of chars as like the character L or the character, the question mark, that kind of stuff. But under the hood, the way they're actually built is as a number. Booleans are the same way. In older languages like C, Booleans were either a 0 or a 1. Okay, 0 or a 1. Realistically, we saw binary last time. What's the smallest number of bits necessary to represent a 0 or a 1? 1 bit. 1 bit. So a 0, we'll just do it right here. The binary number 0 is that. The binary number 1 is that. I mean, you could put as many bits as you want before that. You could throw as many bits as you want before that. That's still 0 and 1. This is 1 times 0, which is 0. This is 1 times 1, which is 1. Because this very first bucket here is 2 to the 0th power, or the 1's place. Does that make sense? So we actually only need 1 bit to hold a Boolean value of 0 or 1. Now, the problem is languages have to be built in terms of their own primitives. Now, that doesn't mean that they couldn't have made a special caveat for a language and actually stored it as a bit, but realistically, Booleans would be stored as 8 bits. So really, we have 7 bits of wasteful memory there. So 8 bits, 8-bit unsigned number, of which the first 7 bits are completely ignored. Because we only care about that final bit. Is it a 0 or is it a 1? Make sense? So built into this typically is some wastefulness, assuming it uses a bit or 1 byte, as and we did talk about that, right? Bits to bytes. So we have a bit is a 0 or 1, a byte is 8 of those. Okay. So it would be an 8-bit unsigned number because we don't need negatives. But in the end, this guy translates to, so it holds zeros and ones. That's what it holds. But it will translate to true and false. Kind of like chars get mapped to characters, zeros and ones get mapped to trues and falses. That make sense? Zeros and ones get mapped to trues and falses. Okay, let me just remind myself here real quick. So in our typical programming languages, the way we define a variable is type followed by variable name equals value. All right, now let me check something here. Yeah, we'll open it here in a second. Actually, let me open it right now in case we have a update we have to run. Finally, we're going to start looking at some tools. All right, well, that's updating. What I'm going to do is I want to show you in a language like Java defining a variable. So let me just, and you will not have to do this in this class. I'm showing you the example of syntax, programming, modern programming language stuff, and then how we emulate that in GameSalad. Next semester, you'll be doing this a lot. So typically, your very first program you ever write in any language is the proverbial hello world program. And this will display hello world to the screen. So I hit play. There's hello world. All right. But now we want to go ahead and let me just make sure we get this. All right, we're good. Okay, so we have hello world printed to the screen. Before we go on from there, let's go and look at the equivalent with GameSalad. So here's GameSalad. We're going to start a blank project. And just real quickly, let me... So GameSalad you can get from a website called GameSalad.com. It's available for both Mac and PC. So you just click download, and you want to get GameSalad Creator. Okay, you have to say you're 13 or whatever. If you're developing on Windows, you click here, and you can download the Windows version of this. I think I mentioned this before, but the Windows version is more primitive than the Mac version. This was written for Macintosh first, but you will be able to do all your homework assignments on the Windows version. Okay, so you're not horrifically limited, but the Mac version really is probably better. And I don't think it's available for anything else. Yeah, you can test your stuff on Android and iOS devices, but we'll get to that later. So you'll download it, install it on your computer, and you have something that will look like this. We're going to go ahead and create a brand new blank project. All right, and so when you create your project, you give it a title. We'll just give it a stupid title right now. And then you can also choose what platform you're writing this for. So iPhone landscape, portrait, iPad, Kindle Nook. Oh yeah, I would spend a lot, or not the Barnes & Noble Nook rather. I would spend a lot of time writing Nook apps. Same thing with Kindle Fire. Don't waste your time with these. Kindle Fire Nook more so than Kindle Fire. Kindle Fire will at least be Android, but you really want to write Android or iPhone stuff. And then they have ones that you can write just for natively on the machine to run on the Mac or the PC. Now, realistically, what does this mean for us initially? It just means how big our screen is. Okay? How big of a canvas they're going to give us to do our game on. We're going to pick iPhone landscape just because that sort of kind of maybe makes some sense and will fit on our screen reasonably well for anybody's, no matter what your resolution of your monitor is. So we're going to pick iPhone landscape. You can choose resolution independent, so it doesn't actually matter, but we don't care in this particular case. Okay? And then you can give a description, but I think the current description is perfectly acceptable. Now, we have 4 tabs here. So we have our project info, we have scenes, we have actors, and we have tables. Now, our scene, think of this, so GameSalad tries to present itself as kind of like making a movie. All right? So if you think about your video game is a collection of a bunch of different scenes. So if we kind of go back to the Super Mario Brothers days, the first scene would be the character select, 1 player or 2 player, choosing Mario or Luigi, although I don't think they had names back then, did they? It was just the red guy or the green guy. But in any case, then when you hit start, it loaded scene number 2, which was level 1. Okay, so you played through level 1, which would have been another scene. At the very end, you jumped and hit the flag, went down the flagpole, and that was the end of that level, which would then load probably another scene that showed your points adding up, how many points you earned that particular level. Then it would load another scene, level 2. Make sense? So the Mario game was written in terms of a whole bunch of scenes. Start the game scene, the accumulate point scene, which probably is reusable because it's always the same. After you finish a level, it's always that same scene that shows your number of points for the number of coins you picked up, kind of accumulating. But each level is its own scene. Okay? So GameSalad calls those scenes just like a movie. They're scenes in a movie. Actors, these are the things that are in our scenes. So actors can be, Mario would be an actor. The little mushroom and turtle guys would be actors. As well as, like the, well, first of all, before I go any farther, has everybody in here at least seen Super Mario Brothers? Like, this guy's talking about flying turtles. Okay. But another example would be the inanimate things on the screen. So, for instance, the pipes, the sewer pipes, those would be actors. The clouds would be actors. Anything we see on the screen would be an actor. Some actors are active. Some actors are there just for show. That makes sense? But in GameSalad, they are all actors. Finally, we have something called tables, and we're not going to deal with tables too much at the beginning, but tables are our way of remembering things between scenes. Okay? That's actually only about a half-truth. It allows us to do some other things too, but I can't really explain those right now because we don't have a context for it. But tables are really powerful, and the early versions of GameSalad did not support them, which actually really limited the types of problems we could solve with GameSalad. Similar to how we talked at the beginning of this course about if we didn't have our memory, if we weren't able to ask questions, if we couldn't do repetition, how many problems could we actually solve? So it was a limiting factor for us. All right? But initially, we're going to be looking at things in terms of scenes and actors. All right? So I'm going to go to our very first scene. Going to look like this. And I'm going to go ahead and I'm going to, over here is our thing called the inspector. And these are where you keep your actors. I'm going to go ahead and hit a plus sign. We'll drag this actor out on the screen here. Okay. Now I'm going to go ahead and I'm going to double click on this guy, which allows me to edit this actor. So think of this like if you're the director of a movie, you're talking to one of the actors, putting their wardrobe on them, telling them what they should look like, telling them how they should act, that kind of stuff, okay? So we're going to take this blank actor, and something we are going to do is we are going to add a behavior to him. So down here we have something called behaviors. So we are telling our actor, look, I don't want you to do much in this scene, but I would like you to display some text. Okay, so we're going to drag the display text behavior here, and notice it defaulted to hello world for us. Okay, and we probably want to make the color of that something dark since our actor is currently a white block. Did I select it? There we go. All right, so now we have the hello world text that will display. So I can go ahead and hit back. So that's our actor. Now before I do anything else, notice I edited the way this actor is. So this actor, this generic actor, displays on himself hello world. So I'll go ahead and drag him out here, and we'll hit the play button to preview our scene. Okay, I would probably need to make that actor a little wider. We can do it right here if we'd like. Just resize them. So there's our hello world. Now, I made a point saying this was the generic actor over here. Now we actually have the actor in the scene. Well, I can go over here and put another one of those actors out here. I put a second copy of that guy out there. So now we have two separate actors on the screen. Both of them follow the rules that we gave to the generic blueprint for that actor. That makes sense? So we can just keep putting those actors in our scene and they'll all just display text hello world because that's what we told them to do. Make sense? Now, what we're going to do here, just to kind of take you through some of the paces here, I have this, we're going to call this guy blueprint, just for the sake of our example here. So this is the blueprint. Anytime we drag this guy out here, a brand new one of these is born. So every single time we put him out here, we have another actor that just displays the text hello world. Okay? Now what I'm going to do here is these guys are already in the scene. Now I'm the director. So I'm going to run out there into the scene and say, look, come over here. Come over here. I want you to act a little bit different than the normal dudes. So we're going to double click on just this guy. And notice this says the behaviors by default are locked. Okay? So I'm going to tell, like, no, trust me. I want you to act different than the other guys. So we're going to unlock that, and we're going to have this guy say woot. Okay? So now, only the director kind of went and whispered in his ear. Only the director knows he's given this guy special instructions. So now, when we go and we run this, we see that this guy will still say hello because he's based off the generic blueprint. But this guy has some special instructions. That makes sense? So we added a specific actor. We would call this guy, just to kind of give some context here, actor. So scene is where the game is taking place. Actors are participants in the scenes. Actors are initially defined as a blueprint. All actors added to the scene from the same blueprint will act identically. If we're connecting this to object-oriented programming languages, each actor added to a scene would be an instance of that actor. Now, for actors, if we are giving us some object-oriented programming terminology, actors are objects in object-oriented languages. So next semester, or even some of our examples in here, if I say an instance of an object, we are taking a blueprint and creating a copy. We're building that, we're using that blueprint to actually build us an object. And in GameSalad, those objects are called actors. Okay? And we're adding it to the scene. Similarly, I can create a blueprint in Eclipse, in Java. So here, let me just go ahead and do this real quick. Call this guy an actor. Here, let's say this. So I'm going to create an actor blueprint in Java. So this is an object called actor, and he has a single behavior, single method called display text. And what this guy does is it displays the text that I told him to display. That makes sense? So now, out here, I can go ahead and I can create actor A1 is equal to new actor. Actor A2 is equal to a new actor. I could say A1 dot display text, A2 dot display text. So this adds them to the scene. This calls their display text behavior. It's the equivalent in Java. Okay? So both of these guys will display the text hello world. So we'll get two hello worlds on the screen. Okay? Now, what we're going to do is we're going to give actors an additional ability that's built into the actors in GameSalad. So we're going to say so we've given this guy the ability for the director to come in and set the text we want an individual actor to display. All right? So very similar to what we did over here, where we double-clicked on this guy and we said, hey, I want you to display something different. Make sense? So now what we're going to do is we're going to go back into our scene. So we probably should have called this guy scene, but in this case, driver is scene. And we're going to say, A1, set your text to woot. We only told A1 to act a little differently. So now A1 and A2 will still call their display text behavior, and now one of them says woot, the other one says hello world. Make sense? So we're mimicking that in GameSalad. But we see that in Java, we had to write, I mean, this isn't that much code, but several lines of code to make this work. Where in GameSalad, we just had to drag a couple things out on the screen. Okay? So we kind of understand the roles of scenes and actors at this point, at least at the basics. All right. Now, let's go back into this. Variables in GameSalad. Now, I've already shown you a variable in Java. We talked about the generic syntax for defining a variable. That was up here somewhere. Syntax, the type, followed by the variable name, followed by an equal sign, followed by the value. This is the generic syntax for defining a variable in C-based modern languages. So right here inside of our actor, see we have a variable defined right here. The type of this variable is string. The name of the variable is text to display, equal sign, and here's the value, hello world. That make sense? Okay. So I'm going to go ahead just for right now. I'm going to remove this ability here, this set text. Simplify this guy a little bit. And now what we're going to do is we're going to say A1's text to display is equal to woot. So now what we did is we just directly changed the value that his variable held. So A1 has his own variable called text to display. Here's that actor. That actor keeps track of a single variable here called text to display. And we told A1 to have his variable act differently. So now they'll both, one will say hello world, one will say woot, same output as before, but we accomplished it a little bit differently. All right, so this is using variables in Java. Now in GameSalad, variables are accomplished through something called attributes. Okay, something called attributes. So what I'm going to do here is I'm going to go back to our blueprint, and I'm going to double click on it. And notice here we have this list of attributes. These are things that all actors have built into them by default. An actor has a name. It has a time. We'll talk about that at a later point. It has a position on the screen. It has a size, a rotation, a color. We can associate images with it. So a bunch of stuff that actors already have built. We also have motion and physics and stuff like that that we'll be talking about quite a bit. But now what I want to do is I want actors to remember an additional thing. I want to add my own variable to this actor. So I'm going to hit this plus sign, and I want to add something of type text. That's kind of like a string in Java. So instead of saying string text to display, I'm going to call this guy text of type text. And I'm going to name this. So notice it shows up as new attribute here. I'm going to name this as text to display. That's the name of my new variable, the name of my new attribute. And now I'm going to give it a value. Hello world. Okay. Now, come back here. I'll hit play, and we're going to have the exact same output we had before. Why is that? Well, maybe I should go in and change this attribute to Bob. Does that mean I'll have Bob and woot now? I'll still have hello world and woot. It's because the behaviors of this actor are hard-coded in. This guy says display the text hello world. It doesn't say display the text contained within this variable. So we're going to go ahead and change that. So instead of just hard-coding this behavior to say hello world, we're going to press this little expression button over here on the right. And through this, we have this thing called the expression editor. We can use some of these drop-downs. So I'm going to click on this drop-down here. We're going to go to our blueprint. This is the source of what we're looking for. So we're looking for this blueprint's attributes. And he's going to have an attribute in here called text to display. Double click on that. So now what we're doing is the text we're going to display is this particular blueprint's text to display variable. That's what self.text to display means. This particular instance of the blueprint. It'll display his version of text to display, whatever value that holds. So now when I hit preview, we have Bob and we have Bob. But wait a minute, didn't I give that one actor some additional knowledge? I had changed this guy, didn't I? Okay. This behavior modified. So behaviors that you got that were shared between the parent and this guy stayed the same. But notice when we changed it at the parent level, this guy shifted as well. Now, having said that, what if I go back to the parent and instead of saying text to display, I just say cat. So we'll tell it to display the text cat. That's weird. So I changed the behavior at this level. Well, what does this guy look like? This guy says cat. This guy says cat. What do you think's happening? Before I go any farther here, I'll drag another blueprint out here. What does this blueprint say to do? This blueprint says cat. I could take that guy away, put a new behavior out here. Let's have it say cat now. Preview. You get nothing. Go back here. Drag the blueprint out there. Still nothing. Why is it nothing right now? Color, I put a new behavior in. So the color is white. Let's change it to black here. Now we'll run it. And we see we have our cat. I'm going to go ahead and add another guy here. We'll see we get two cats. Now, this has to do with the behavior display text. Okay? This is a persistent behavior. And what happens is because this is a game engine, it's made for performance. Okay? So, persistent behaviors, if I want this guy to display text, rather than it, we have something we're going to talk about called the game loop. So as our game is running at 30 frames a second, let's say, 30 times per second, we're going to loop through the game loop to find out what should update on the screen. Well, we don't want this guy constantly updating hello world or cat or something like that on the screen because we're going to see a flicker. Instead, we want it to cache that value because it's a persistent behavior. Once it gets set, it just is. Okay? So these guys in our screen, in our game, were cached. So even though we were making changes to it, it was stuck on the old value because we didn't refresh our game. We would have had to close this and reopen it to get the changes to happen. Okay, because we're testing. Now, the reality is this is the advantage of using variables so we don't have to deal with randomness like that. So what I'm going to do, we're going to go ahead and get rid of these. I'll go into Blueprint. We're going to change this to again be our Blueprint's text to display variable. Throw that guy out there. See, it's currently Bob. Throw this guy out there. Now we have two Bobs. Now what I'll do is I'll go into this version. And notice that I can go over to text.display. And I can change that to hello. Now I've made this one is Bob and this one is hello. But now the important part of this is notice that in order for me to do that, I did not have to unlock this object. So it is still governed by the top level blueprint. The second I go and I unlock this and make changes to this guy now becomes a unique object to our base. That makes sense? We have an ability here to revert back to the prototype if we'd like. I called it a blueprint. He calls it a prototype. Okay, so now we're back to the original. Now, can you think about an example in a game where you might have a blueprint that you use, and then you might have a special version of that actor that you would unlock and add some additional features to? Pretty common example in a game. When we think of a video game that has something called like boss fights, what do we think about that? What's a boss fight? A stronger version of what you've been fighting. So we might have been fighting a whole bunch of little mushroom guys or flying turtle guys, and at the end of that level, we might have a giant flying turtle guy. So that boss would be bigger, so his size would be larger, fine. But do the bosses typically have other abilities? So normal flying turtle guy, some of them shoot little fireballs? But the boss might throw ninja stars or something, right? Okay, so the boss has some additional abilities over and above the regular. So we might go in and, at the boss scene, we might go ahead and add in an actor that we've had all along that has a whole bunch of standard behaviors, change that guy to have some modified behavior specifically for that boss. Kind of make sense? Okay. So now, both of these guys are based on a behavior. And that behavior is based on a variable. That makes sense? Now I'm going to go into the blueprint here. I'm going to change the value of that guy to cat now. So I've changed the value of the variable to cat. Now let's go and look at each of these individual guys. This guy, his value says cat. This guy, his value still says hello. Notice that this one is in white over here. It shows that I have manually modified this. That makes sense? Whereas the previous one still had it in gray. It's not unlocked, but these variables are local to this particular guy. Just like I did over here in Java, I changed this individual actor's text to be woot, when the default was hello world. Now when I run this, now we get cat and hello. See the difference in behavior we got when we used the variable for the caching rather than a hard-coded value? Every time it runs, it's still going to pull from that variable to cache the value. As opposed to before, when I gave it a literal, it created a space in memory with that value in it and said, okay, from this point forward, I'm always going to display that value. We would have needed to close down the game engine and reopen it for it to refresh that. Okay, so punchline, use variables in every single circumstance where a value may change. Because variables allow us to mimic memory, and they also allow us to vary the value. Make sense? All right, homework assignment for Wednesday. Download GameSalad and get a Hello World program working. That is an actor that is on the screen that displays Hello World from a variable. Make sense? I'll go ahead and put it up on Angel. I'll give you a link to GameSalad just in case you didn't write it down either. All right, I will see everybody on Wednesday.